This is up. Hello, hello. It is, right? Looks good. Thank you. All right, so let's get started. Last lecture, we talked about basics of probability. You learned about basic concepts of probability. What is a probability distribution? What is the probability mass? Probability mass, it sums to 1. You know all that. We also studied a few sample statistics that are computed from data, namely the mean, the median, variance, standard deviation. Yeah, everybody good? Recollect that? Okay. So the next 2 lectures, this one and the one on Friday, will focus on applying some of these concepts in practice using a computational tool, right? You could use, we are using Python here, but you could use any other framework you want, which is also suited for data science. Anyone know a different framework for data science that you might use, which is pretty popular? Yes. Anybody else? Yes. Octave, MATLAB. You could use any of these either. Python is actually pretty well suited for data science. There is a large variety of toolkits that are available, which actually make the process of data science pretty quick and fun. The fundamental advantage here is that it's really, really quick to prototype stuff in Python. So note that you're playing with data, and you don't really know, or you may not really know what you're looking for. This is not a production environment where you want to deploy something at scale. So in such scenarios, it's useful to use languages which are very quick for prototyping, dynamically typed. You don't have to declare variables up front. So Python allows you all this flexibility, and this is kind of why it's useful to learn Python. So everybody seen this XKCD comic? Anybody here? No? Okay, so you should definitely take a look at this. There's a guy who's flying, right? All he does is import anti-gravity. Okay? All right, so let's get started. This is going to talk about Python for data science. This is not a Python 101 course. Although Python is fairly simple to learn, there's a tutorial right there. Most of this class we'll learn by example. We'll talk about what toolkits exist in Python, what packages exist, which especially make it really well suited for data science. Are the goals of the class clear? This is what you'll learn at the end of the lecture. Yeah? Okay. We'll learn by example. At the end, actually, we'll spend about 45 minutes trying to actually solve a data science problem. So you will actually see all of this applied in practice, and you will see how it's really well suited. So everybody familiar with this picture, or at least these 4 steps of what data science is all about? No? So what happens? What happens in data science? First of all, what happens in science? Can somebody describe the scientific method? Anybody? The scientific method in school or high school?
I think you have a hypothesis.
Sure.
And then you set up an experiment designed to test the hypothesis. And then the results of the experiment will determine if the hypothesis is true.
Perfect. So this is what we call empirical science, right?
Yeah.
Perfect. So this is exactly very similar to that, except that now we're operating primarily with data, right? So you have some data that you have analyzed. These could be observations that you yourself made. But what is this? What are the questions that this data motivates to answer? That's the fundamental idea, right? So you're a scientist again. So you want to say, how can I answer this question? And you do this primarily through data, right? So the first step here is to actually gather data. Now there are multiple ways of doing this. You could actually go and approach every single person if you're saying making an experiment. Let's say you want to get data on the heights of people in the US. You could collect a bunch of 100 people, go and ask them what is your height, right? This is a survey method. You could do this. You could always go to maybe somebody else has done it for you. Maybe the CDC has done it for you. Maybe the health department has done it for you. Maybe a million such records are present. You could just download them from the web. So there are different ways of getting data. Once you get the data, you will notice that data in the real world might really be noisy, right? So if you're dealing with textual data or even images, it's not clear that data is really, really useful in its raw form for processing. So you need to pre-process it. That's the second bullet here. Yeah? Any questions so far? The third step, as you mentioned, is analysis and modeling. So you might say, let me posit some model of this thing, right? So how does this work? We don't really know, but we could posit some model, or at least come up with a few hypotheses that we would like to test, right? Is this clear? So in the case of, let's say, is Donald Trump going to win or Hillary Clinton going to win based on tweets, right? Who has more followers? This is one particular thing you want to test. How do you do this? You go to Twitter. You basically spider all of Twitter, get all of the tweets that people tweet about. Look at where Hillary Clinton is mentioned, people supporting them, people supporting Donald Trump. Then to make a hypothesis, figure out if there is a difference, right? Is this clear so far? Okay. We create such a model. And then once we have a model, we evaluate it, we present our results, and then we answer the question. So far so good? Okay. Now, all of these 4 steps, Python provides rich toolkits for each of them, and they are very succinctly represented below here, right? And we'll talk about each one of these boxes briefly, right? And so this is how I'll walk you through the entire process, and then at the end we'll actually solve a problem. Okay? Clear? So how do we get data? It's because we are looking at data. As you mentioned, we are trying to solve a research question, right? And for that, we need to get data. How we do that primarily is to make observations. That's what an empirical scientist would do. If you're a physicist, you would actually get your apparatus, and then you would perform experiments, get data, right? We are doing something very similar, but our data might come from different sources. We might not really have an apparatus per se, but you could call the entire internet and our computers as apparatus. Is the analogy clear? So instead of Galileo pointing his telescope to the sky, we are pointing it to the internet. Is it clear? Okay. So there are several toolkits available for doing this. Beautiful Soup is an excellent toolkit that is available in Python. It's very, very widely used, especially for scraping and HTML content. So you have HTML pages, and you would like HTML. Everybody knows what HTML is. Hypertext markup language. That's all the content your web pages are made up of, right? Now, all of these web pages that you want to scrap are essentially HTML code, right? They're essentially HTML code, and it's going to be hard for you to write extract out elements from this huge mass with a lot of effort, right? It's going to be a lot of effort to do this. Beautiful Soup is a library which will allow you to do this very quickly and very, very fast. If you want to parse XML, you can do the same thing using Beautiful Soup too, or using LXML. Tweets. Anybody playing with tweets around here? So Tweepy is an excellent toolkit for Python for spidering tweets. All you need to give it is a user handle, and it will essentially spider tweets for you. And of course, Pandas. Anybody knows what Pandas stands for? Python for data analysis. So all of this is, a lot of stuff is there in Pandas which you can use. And you could actually, I will go over Pandas very quickly also in later. All right. So let me show you a very quick example of what Beautiful Soup can do. Again, so several Python packages are easily available to scrape and download data. Here is a very quick overview of things you might want to do with Python. And if you are doing any of this, there are tons of toolkits out there. Just search for them. Anybody on Reddit here? Reddit? If you want all of the comments on Reddit, you want all the posts, you can actually get them through this Python toolkit, PROM, okay? Wikipedia, also you can get. All of Wikipedia is available as a dump, but you could even, you have Python toolkits to efficiently process Wikipedia. And Stack Overflow. So if you're ever looking at a data science project which you want to do, all of these are very good sources for data. Any other questions on data itself?
So can you actually, are these data for public usage? Like
Most of Twitter is Reddit, the comments is, Wikipedia is public under the Commons license. Stack Overflow has released its own data set for that also, it's all public. Other stuff, you have to check the licensing conditions, okay? Remember again that Twitter itself, you may download the data, but you may not post it yourself. You know, you don't distribute.
I have a question.
Yes.
Sometimes these APIs have a lot of restrictions. Like I know Tweety has a restriction that it allows you to download only 7 days worth of data. And like,
Pardon me, what?
if you are downloading some particular handles data, you can only download up to 7 days of data.
Yes, that is true. Also, you must remember that this is a very small sample. You might get something like a 1% sample, right? Or you might get a 10% sample if you're really lucky, right? But you will realize that this is one of the good things about big data in the sense that when you have such a large sample, even with 1% of the data, you can do something really, really cool. Now, if you want to get access to data which you don't have, then you will have to look at proprietary methods to do it. Now, if you might purchase a license, or you might actually pay Twitter some money to do it. So consider the perspective that you may not just be a researcher who is working standalone. You could be in an organization which has access to this data, which will allow you to do this, right? But the power of open data is actually pretty powerful here. And even if you have 1% data, you can do something really well, as long as you interpret it correctly, as you will see now. Okay, so here is a quick example. You have IMDb. Yeah? You want to get, so now what happens is, you want to build something, maybe an app, and you want to say, I type in the name of a movie, and I want you to tell me who are the actors and what characters they play. Okay? So in this particular case, in Shawshank Redemption, seen the movie, everybody? It's a great movie. Okay. So Tim Robbins plays Andy Dufresne. Morgan Freeman plays Ellis Boyd Redding, right? And you want to get all of this data from IMDb. If you go to IMDb's page on Shawshank Redemption, you will see this list, the cast, right? I want to extract out both of these text fields and print a list out. Is the problem clear? Okay? How do we do this? In Python. It's probably 10-15 lines of code, very short. Here's how it goes. Is everybody able to see this at all? No?
Not the blue.
Not the blue. Let me see. There must be a way to command plus. Okay. Sorry. Where are we now? Whoops. Let's go back. Now? Yes. Lights, dim the lights. Let's see, how do we do that? No? Okay, that was not good. Better? All right, so very, very quickly, right? Very easy. I talked about beautiful soup and how you can parse HTML content. So the first line just points to the link of the web page, right? Requests is a module in Python that will download the content on that web page given a link. So requests.get is essentially returning you the HTML code, right? All of it that is present on that page. What do you do now? You import beautiful soup, you pass in the page, that all of that HTML content you got. What it will do is it will parse all of that HTML and put it into a tree format. And it's an object, right? And now you can actually iterate through all of those tags very easily. For in this particular case, I'm looking at all places where the tag tr is present. So this is all rows in this table. You saw this table below? All of these are rows in this table. we get each row. Note how very quickly I just do soup.findAll. I don't necessarily write code to look at the string or do anything of that kind. Note again, so this is very, very quick. I just do soup.findAll. It will return me a list of all the places where the tag tr is present. I go there, I extract out the value of the property whose item prop is name and and character. So there are names and characters in the HTML, right? I just get that. The text attributes of that is what I get, which is essentially Tim Robbins, Andy Dufresne, right? And all I do now is print them out. Is this very clear? Just 10 lines. Yes. I'm sorry? Oh, because tr is essentially giving you, so what you're doing is you're finding something like this. The thing consists of something like this. Character 1 maybe. Let's say row 1, ntr. Row 2, ntr, right? I want to get all of these, not just one of them. So I just don't want Andy Dufresne and Tim Robbins. I want Morgan Freeman and the other guy also. So this is, when I do find all of some tag, it will find all of these, right? And return to me each of this guy. And each of this is an actor-character pair. Yes. Is it clear? So this is how you get it. I'll show you some more interesting examples, but is this example clear? Just 15 lines? Yes. Okay, so this is very, very simple. All you need to do is, there are methods to do it, depending on what you want, but you must know that Python provides you ability to pass in the link via command line. So you can decide whatever you want to do. Alternatively, you could read all of these links from a file. Let's say you have 10,000 links you want to get. You put all of them in a file. You read every line of the file, and then do this. Very, very simple. I'll show it to you.
I have to note down all the links.
Not necessarily. So it depends on what you want to do. Let's say you don't have these links. You have the top page of IMDb. Okay. So there will be a link there for the top 100 movies or the top 10,000 movies in IMDb, right? You go there. You spider that content. Open that link again, right? So you can spider it. And remember that all you're doing is parsing HTML. So all of this allows you to do anything on that page which you can see in HTML, right? So you don't have to parse HTML. It will do the parsing for you. You just have to write the logic. So how would you as a human do it? You would go to imdb.com. You would click on, or you would fetch IMDb top 100 lists, right? And then you would go again doing this. You could do all of this automated, right? Imagine a block on top. All it does is fetches the top page of imdb.com, fetches the link corresponding to the top 100 guys, and then iterates through them, right? Is it clear? Is the answer clear? Yeah.
Is Scipy similar to this?
Scipy is similar, but Scipy is more like a toolkit which will, given a root URL, will get all URLs that you can do a DFS from, right? It's just going to download all the content and put it in one place, right? It doesn't do any parsing per se. All it does is spidering, right? What you want to do is you want to download but also do a bunch of parsing.
We need to use both of them together.
Yes, so you could in principle have one component which uses Scipy, get all the web pages, store them to disk. This component could read all of those files individually, parse them, and do what you want, right? Any further questions? Yes.
So before this snippet, I guess you have some kind of header to bring the beautiful soup into context?
Yes, just say something like from BS4 import beautiful soup. Okay. I will post all of this code. So again, all of this is will be available on the website, so you don't have to worry about this, including the full code. So I'm just showing you the snippet to make things easier, okay? All right. Any further questions? Yes.
Item prop equal to name and class equal to character. Does it represent some like?
So if you go to the HTML page, yes, if you go to the HTML page, in the HTML code, you will see something like item prop is name, then the name would be Andy Dufresne or whatever. Character would be Tim Robbins or whatever, you know.
So you need to know it.
Yes, so what you need to do is you need to at least find out what the structure of the page looks like. it will do the parsing for you, but you need to query something, right? So you need to know what it looks like. This is website specific again. You go to a different website, you have to do something different, right? That depends on that. But this is a framework that allows you to parse everything together and which you could use very quickly. Note that I didn't have to write all the HTML parsing code, right? All I need to tell it is extract out the text characteristic of item prop name, right? So you just need to know what you want out of that, and you can get it. All good? Okay. Let me move back to normal resolutions. Okay. So we talked about the first step in general about pre-processing, about gathering data, right? The next step is how do we process it? So now you will notice that most of your data could either be a table or a CSV, right? So Pandas is an excellent framework for that. Pandas can handle CSV, tab-separated formats. It can handle HDF5, compressed formats, a bunch of things, okay? So very, very versatile framework. Now, what is Pandas exactly? Anybody use Excel here? Excel? Yeah? Pandas is essentially spreadsheet software for Python in a nutshell, right? So whatever you can do in Excel, you can do in Pandas and in a much more versatile way. So there are only two major things you need to know about Pandas. One is how does it represent a table, and how does it represent a one-dimensional array of numbers, okay? A table is what is called a data frame. So it is something like this, right? This is a table with rows and columns, right? So this is A1, A2, A3, headers of the columns. Yes?
So like when we parse a file, CSV file using Pandas, and then when it creates the array, it will strip off the first header row.
No, it will not. If you specify a flag called header equals none.
It will keep it. Okay.
Yes. So you have to be you have to read the documentation. So again, all of these Python toolkits have excellent documentation. Click on read documentation. Click on get started if you don't know what it is about, and it'll tell you exactly what it looks like. So if you say something like header equals none, it will tell you it will imagine that there is no header, so it will get everything. So imagine you have again. So very quickly. Actually, wait, hold on. So let me do one thing for you, because we need it anyways. .edu60059, right? Okay. Boom, boom, boom. Here's how we do this. Import pandas as pd, okay? pd dot read CSV. You see how it shows you this?
How do you get that lookup?
Shift tab, right? And it tells you very clearly header is infer, which means that it assumes that there is a header there.
Right.
So if you want all of these rows, you can say header equals none. Then everything will be put.
But when you convert it into like a data ND array for use with Scipy, it will strip off that thing, right?
You have to specify what you want to get out. It will read everything.
Right.
Then you have to specify what you want.
When it is within Pandas, within that module, it will retain
Yeah.
the header.
Yes. If you want, yeah, that is correct, right? You don't want to pass the header to Scipy. Scipy doesn't understand that. We will see what it looks like. It's an ND array.
Yeah.
You don't want to pass in something else to it.
But then it becomes just an index, right? When it comes to Scipy, you have to remember which column.
Yeah, but we will see how it looks like. It's not that hard. So hold on to your question, and you'll see how easy it is. Okay, so this is how it looks like, right? And you can always look at the documentation right here. Again, click on plus to see more. I'm assuming you guys have set up IPython notebook. It was, I think, a prerequisite or mentioned in this thing, right? Okay. All right, so you can easily load CSV files. How do you load TSV files? Tab separated. You see the separator flag here? This variable is separator. It's set to comma right now. You set it to a tab and it will load tab separated files very quickly, okay? So I would suggest that you experiment and get very comfortable with Pandas throughout this course. This will make your life very easy. All right? Now, what will happen is, I already told you how you can load CSV, TSV files. Now, what happens if you have a machine with 4 gigs RAM, but you have to process 20 gigs of data in CSV format? Anybody? Okay. So you can load all of this in chunks, and you can iterate through these chunks. So you can load, say, 100 rows at a time, right? How do you do that? So you can specify something like chunk size here. It should be a part of this thing. So chunk size equals none, right? You see this? Specify a chunk size, and you can iterate through chunks. So what happens is you can load only 100 rows in memory, process it, do what you want, right? These are all parameters that you can pass through to read CSV. A bunch of them. All of them, so most of them have default values. But if you want to do anything specific, you can do it, right? You can. So no, it's also very, very powerful. So if you have like a date field, right? So something like, you have a table where you have person, birth date, right? In DDMMYY format, right? This is a CSV file which you could load. What you can do in Python with this function is you can specify that this column is a date. It will actually parse the date out for you and put it into a date object. So you can actually get year, month, and day automatically. You don't have to split this as a string, figure out what the date is, the month is, and the year is. Is it clear? So it's very, very powerful. Yes?
Just to make it clear, this chunk size is number of rows or is it MB or actually?
Right. Okay. So my bad. So this is going to be how. It's not going to be number of rows. You can specify something like 10,000. No, not MBs. 10,000. It doesn't. It's not about the size of the thing itself. So let's say your file is 1,000,000 rows. You can load 10,000 rows at a time. That's what this is. It's not the number of bytes as per. Okay. To be clear. All right. So I would encourage you to explore all of these options, but this is how you can use Pandas very, very quickly. Now, what else does Pandas provide you to do? You can actually use it for SQL-like operations. You have 2 tables, right? This and a different table like this. So let me give you an example of what I mean. So you have a table with student ID and name, okay? Foo, not foo, let's say 1, 2, 3, foo, 3, 2, 4, bar, okay? A different table with student ID and let's say age, whatever. 1, 2, 3, 34, 1, 2, 3, 45, okay? You want to join these 2 tables based on student ID. So what I want is a new table where I have student ID, name, and age. Okay? This in SQL is called an equi-join. Yes, anybody? Equi-join. Familiar or not? Okay. So we just want this thing to happen. So you want something like 1, 2, 3, 3 to 4, foo, 34, bar, 45. How do you do this? Again, very, very simple. PD dot merge. Pass in the first data frame, the second data frame, and that's it. And specify how you want to merge it. So you could specify any column here. You see this on keyword? On is a list of columns you want to merge it on. So in this particular case, I would be typing in this code, right? I would be saying pd dot merge. So let's call it student data frame 1, student data frame 2, on student ID. Is it clear? That's it. This will create this table from these 2 things. Yes? So there are a bunch of these things. You can merge in many ways. You must know that there are 3 types of joins, right? Inner join, outer join, equi-join. All of this is supported here. You can merge many things on different columns. You can say what you should fill columns which are missing with, right? So when you do an outer join, you might find that there's a column which is not there in the other one. What should I replace it with? All of this are all parameters you can pass here, right? So you just need to know how to call these functions. Clear? Everybody so far? It will actually even allow you to do a bunch of data analysis. We talked about the summary statistics, right? Did we talk about the summary statistics? Mean, variance, last class, yes? Yeah. Okay, let's go and see how to do this. Very quickly, let's open up maybe Scipy. No, maybe not. Let's see. Okay, let's do this right here. So I'm going to create a data frame which is going to be of the following form. See how I create a data frame here, yeah? Watch. Records. A1. B2. C. Oops. So this will know that you can actually create a data frame from records. Records are basically tuples. So watch how this works. So now if I show you what records is, oops. All right, let's see very quickly. Records, shift, return, right? You see this? Now, all I do is df equals pd dot data frame. This is constructing a data frame from records. Dot from records, right? You pass in the records. You pass in what columns to use. Let's call it A and score. Let's say score. Okay. You see this? Now it has created a data frame object. You see that? It has 2 columns, A and score, yeah? Now I do something like df dot describe. What does it tell you here? There are 3 things in the data frame, right? Yes or no? What is the mean score? The mean score is computed, right? It's 2. What is the standard deviation? 1. What is the minimum value? 1, right? What is the 25th percentile? What is it? What do you mean by 25th percentile? Yeah, first quartile. Second quartile, what is the maximum? 3.0. Yeah? So you can get all of these summary statistics, the one we talked about last time, very quickly using Pandas. Any questions?
What if you add, so you have added A and score, you can add another C.
Yeah, you can add a bunch of things and it will provide you the statistics for every such column.
So providing, I mean, considering that I only add A and A1 and not more than that, the 2 columns, and then while reading I add A, score and X, then
I'm
what
sorry,
happens?
what?
So I just add a new column in while reading changing it into a data frame. I add A, score and Z.
Okay.
And then what happens after that? After adding Z, I do describe.
So once you add a new column and you describe, it will show you the summary statistics for every column there. So it will show you the score. It will show you this, all of these things computed for score and Z.
Even if that Z is not there in my actual data.
Why is it not there? What do you mean it's not there?
In records, I haven't added.
So records has nothing to do with what happens after that. You have changed data frames, right? So if you add something to the data frame, that's what's going to be used, not records. Is it clear? This is just a method of inputting to a data frame. You could read this, you could create this from a CSV file. I'll show you how to do that also, right? In the 45-minute practical application of a data science problem, I'll actually show you how that works, okay? Cool. So let's go back. All right, so this is how you might load something from a CSV file very quickly. pd.read CSV. You see that? Very quickly. And I'm loading stuff. Okay, let me go back to present. Here I'm loading a bunch of data about the heights of boys and girls at different ages. So boys underscore 2 is the heights of boys at age 2, boys underscore 9 is the height of boys at age 9, and so on and so forth, right, at different ages. And we'll play with this stuff very quickly, right? So I'm loading all of this into a data frame. Is it clear? All right, so I talked about pre-processing, and I mentioned about how we could do this pre-processing, load several data in different formats. Note that if you are doing pre-processing, let's say I had to convert all of these into feet. These are in centimeters right now. I want to convert this into feet. All I do is divide by 30, right? Do it only once. 30 centimeters is a feet. Yes? Is a foot. So divide by 30 all of this and do it only once. Don't do it n number of times. That's one of the most common mistakes. Yes?
Is a data frame just a list with some extra functions?
No, it is not a list. It's actually it's more of an object. Let me put it that way. You could think of it as a map, more of it, like, you know. It's not a list.
Okay.
It's more like a key value thing. They have columns also. So you could do something like this, to be clear, right? So you could say extract out only the score column, and now you will see that to be a list. You see? It's not exactly a list. It's more of a map, if you would, like a dictionary kind of thing. Yes?
You have a huge data frame object. Not all the information is going to be in memory at the same time, right?
So that's what I said. You could load in chunks. You could load 10,000 rows in chunks, depending on your RAM size. All right. In any case, if you are really out of options in that case and you have like terabytes of data, Pandas is not going to be the way. You have to use something called HDF5. It's a method of storing files in a compressed manner and extracting them really easily. So if you look at something called pi tables, that will allow you to do that. Yes. So that now this is a computational problem. How do you compute a mean from a running sum? Yeah, you have to figure out how to do it, right? You can do it. It's not hard. Okay. Also note that you'll have to do different things depending on what domain you're working from. If you are from the image processing world, you have to do something different for pre-processing than text. Yes? Agree? For example, here, textual data. I'm trying to process a document. Anybody know what the first line is from? Which poem, which author, which poet? What is this life full of care? We have no time to stand and stare. No. Daffodils by W.V. Yeats, right? W.H. Davies, right? Daffodils. Anybody read the poem? No? Okay. What about Think of Beauty, the Joy Forever? Fun. What about that? No? John Keats, Endymion. So now I have this entire thing. Note that there is no sentence operator. Like I have just a bunch of things from different poems plugged together, right? I want to separate them on sentences. So I want to say, this is an end of a sentence in some sense, right? I want to split that out. How do I do that, right? I want this to be the case. Very simple stuff. So NLTK is a natural language processing toolkit, NLTK. I just import it, I pass it the sentences, and I call this function called sentence tokenize. It will split up the sentences accordingly and return me 2 sentences. Yes? Very, very, very simple. So if you are dealing with textual data, NLTK is the way to go. Okay, now we're on to step 3. How do I build or infer a mathematical model for a problem, right? And so for this is where scientific Python comes up. So you mentioned here that a scientist would actually frame a hypothesis, and then he would perform an experiment, or he would fit a model and try to find out if this fits correctly, right? So scientific Python is a huge set of, it's actually a stack of frameworks which are very useful for this particular step. It has extremely good capabilities for linear algebra, fast Fourier transforms, signal processing, calculus, and so on, right? So it's very, very powerful, and you just look at Scipy. If you just go on, and you'll find distributions of Scipy. So Anaconda is a distribution of Scipy which is pre-packaged. It has a bunch of things which you can just download, okay? I'll show you stuff. So this is the Scipy ecosystem. I talked about it as a bunch of things. This is the fundamentals. So there are actually 6 components. The first one is Numpy. Numpy is all of the numerical expressions. It provides you it is the let's put it this way. It contains an extremely efficient implementation of an ND array. Okay? So an array is 1-dimensional. A matrix is 2-dimensional. So if you have n dimensions, you can have an extremely good implementation here. Okay. Now you have a bunch of very efficient implementations going on here. Scipy will build on top of this and provide you linear algebra capabilities, fast Fourier transform, signal processing, bunch of things, right? Pandas we already talked about, right? It also uses Numpy in the background. How do you do it? How does it compute mean, right? It stores all of this into a Numpy array and then computes the mean. Matplotlib is Python's plotting library. Very, very powerful again, and we'll see how it works. We'll talk about Scipy in a few seconds. Just hold on to that. And you already know IPython. It's an interactive console for typing stuff, right? So far, so good. This is just the overview. All right. So we talked about the fact that Numpy is more like the lowest layer of the Scipy stack. It contains very good, efficient implementations of an ND array. All of this is implemented in C and Fortran, by the way. The backend is all C and Fortran, so it's really quick and fast. It provides you a bunch of simple statistical operations, like you can compute the mean, the standard deviation, etc. You can do a bunch of linear algebra operations, and I'll show you that in a minute. You can do all of these fast Fourier transforms. So let me show you how this works. I want to invert this matrix, 2, 3, 2, 2. Yes? Familiar with matrices, right? Okay. How do I do this? I import Numpy as NP, right? Do you see this? Everybody seeing this, or should I switch to the notebook? We have both, but it's very easy if you do this. I create an array. This is how I create a two-dimensional array. 2, 3 is the first row. 2, 2 is the second row, right? Now this matrix is a 2 by 2 matrix, right? And then I just look at the linear algebra package of Numpy, and I call invert, INV. It will produce an inverse for me. What is the inverse? This is the inverse. Can anybody verify this is the right inverse? Multiply these two matrices. What do you get? Which is 1, 0, 1, 0, 0, 1, right? Okay. So far so clear. You can always look up the documentation for a large number of these functions that you can use. Yes?
Would you suggest we download the Thought or the Anaconda distribution?
I would suggest to download the Anaconda. That's actually fairly stable, and also a lot of extra stuff is added. Like, it gives you stuff like Matplotlib also installed, IPython also installed. It's very easy. Just make sure you follow the instructions very carefully of the Anaconda distribution. You have to use something like conda install to install packages. Okay? Okay, so Scipy is Python for scientists, essentially, scientific Python, right? It has a bunch of libraries for linear algebra, optimization. Anybody taken a course on linear algebra? Who has taken a course on linear algebra, or at least know what it is? Okay, you must know linear algebra for data science. You won't survive otherwise. Okay. Optimization. Anybody doing non-linear optimization? No? You're the only guy. Okay. Statistics. You will all be familiar now with this course. Signal processing. Anybody from electrical, electronics? So FFT, fast Fourier transforms, wavelet transforms, all of this, right? Special functions. Anybody tell me an example of a special function. Anybody?
Beta function.
Okay, gamma function. Okay, good. So all of these can be easily computed here. You just have to call something like scipy.gamma with a parameter. Will tell you what the value of the function is. But we'll see this. So let's see. Maybe I'll open the stuff here. So let me show you what we can do. Can everybody see this at all? Command plus. Let's see. Okay, this is not good. Let me go back to. So here again, this is the same thing, but look at what we can do. Import Numpy as NP. We create the same array. Yeah. What is this? Axis equals 0 is telling me do a column sum. Do you see that? So this array, this 2D array has two axes. One is columns, one is rows. So axis 0 is this guy. This is just a convention. So axis 0 is this way. So this is saying sum all the elements of this guy, but along columns. And so you get 4 and 5 very quickly. You don't have to do this by iterating through every element. Never do that. That is very, very slow. This is super fast. How about row sums? Axis equals 1. Yeah? Very clear. Everybody here following? Yeah. Okay. Now we go back to our problem of using scientific Python. Anybody familiar with the laws of uniform acceleration? We have a car that is moving at a constant acceleration, right? What is the velocity of this car at time t? So v equals u plus at. Three things, right? This is fundamentals of physics. So v equals u plus at. A is acceleration, t is time, u is the initial velocity, right? What is s? S is the displacement or distance, right? Half at square. And the other one is what? V square equals u square plus 2as. Yes? Everybody familiar with this stuff? Okay. So now we are here and we want to do this in Scipy. We have a car whose velocity at time t is given by 25 plus time t in miles per hour. Yes? What is the distance this car covers in 3 hours? So we just have to integrate this guy. If we didn't know this, right? I'm giving you the velocity. What is the displacement? Integral v dt. Yes or no? Displacement is integral of the velocity over time. Yes or no? Okay, so we just have to integrate this function 25 plus 10t from 0 to 3. Yes? Here is how it's done in Scipy. So import Scipy, import integrate function. We define the velocity at time t to be 25 plus 10t. You see this? This is a function called velocity that takes in a parameter called time t and returns the velocity of this car at time t. Yes? 25 plus 10t. Look at how I compute the distance. Distance is obtained by integrating the velocity between the limits 0 and 3. So look at how this works. This is specifying what the function to be integrated is. This is specifying what the lower limit is. This is specifying what the higher limit is. 0 is the lower limit, 3 is the higher limit. Yes? Everybody following? This will essentially use a numerical integration algorithm. What is a numerical integration algorithm? Anybody heard of trapezoidal rule, Simpson's rule, things of that kind? Okay, this is, so for those of you who don't know this, imagine you have a random curve like this. You have some function like this and you want to integrate this, right? What you could do is, there are many ways. You could approximate this via a trapezoid, or this is how you do this, right? This is called the Riemann sum. Yes? Riemann sum. Everybody familiar with this concept? You could now sum the areas of this. Almost all of these methods like Simpson's 1/3 rule, trapezoidal rule will essentially be approximations of this Riemann sum. Yes? So there are extremely efficient and good stable methods for computing such integrals. And you can look up any textbook on numerical methods and you'll get it. Okay? So the distance is 120 and it tells you that the error is really, really small in this approximation. Yes? Because it's almost trivial to do this. Somebody can verify this. Okay. Cool. So I hope you have understood how powerful this toolkit is. You can do a lot of these things. Integration. I'll show you in differentiation. You can even do differentiation. You can compute gradients. Okay? Now, anybody know the difference between numerical differentiation and, let's say, analytic differentiation? No? So, okay, sure, go ahead.
One is exact and the other is approximate?
Yes, but you could, in some sense, yes, but there's also more to it in the terms of formula. So what is the, suppose I want to compute the differential of y equals x square at x equals 1. How do I do that? So I could do this in two ways. One is I could say that, look, a symbolic method would say, look, I have to compute this exactly in terms of an equation. So I represent this as an actual formula. So I say what the differentiation or the derivative of y with respect to x, dy by dx is 2x. I substitute x equals 1 and I get the derivative of at x equals 1 to be 2. Yes? What is the other way of doing it? Let's say I don't know the derivative of y equals x square. Right? What you do is, you go back to formulas. You say something like this, right? It is f of x plus epsilon minus f of x over epsilon for a small epsilon, right? So this is our limit epsilon tends to 0, right? You could choose a very small epsilon. Choose for the sake of computation. Let's choose epsilon to be 0.1. What do? You put f of x plus epsilon is 1.1 the whole square. Yes? Minus 1, right? And divide by epsilon, which is 0.1. So this is something like 1.21, is it right? Minus 1 divided by 0.1, which is 0.21 by 0.1, which is 2.1, sorry, my bad, right? Close, but fairly reasonable, right? Note that I didn't have to even know what the derivative looks like. I just had to evaluate the function and divide by something. This is what a numerical thing looks like. I don't have to compute the answer in a closed form. I don't know what it looks like, but I can still compute the derivative. That's what, so scientific Python, which we just used here, will compute a numerical gradient or a numerical differentiation. It doesn't know what the actual value in closed form is. But there are toolkits in Python which can even do this symbolically. So let's say I actually want to differentiate a function and I want to know what the exact answer is. Here it is. So this is called symbolic Python, SymPy. This is the difference between symbolic differentiation and analytic differentiation. Numerical differentiation, yes? So here, this is actually going to do algebraic manipulations. So I'm saying import SymPy. Then there are two functions, sine and cosine. And then I'm saying there are two variables, x and y, right? I'm defining a function called x squared plus x cubed plus cos x. You see this? Forget about what I'm doing later. But you see this? This is a function. That is a function of three terms, x squared, x cubed, and cos x, right? And I'm saying, I'm asking SymPy to differentiate this function with respect to x. What does it return to me as output? Here we go. See? Boom, boom, boom. This is an actual exact computation of the derivative in a closed form. You see? 3x squared plus 2x minus sine x. Yes, everybody see this? Yeah. So imagine you're solving an optimization problem where you need an exact answer, and you can do it. You can use SymPy to do it. You can actually find out what the derivative looks like. Yes?
When do we use this numerical method, and when do we use the closed one and then the separate?
So it depends. It depends. So there are some functions which are very complex. So they may take a lot of time to even compute this. Remember, this is done through algebraic thing. So there's a lot of things going on. You may not require an exact answer for some problems. You just need to know what the value is.
Okay. Do you have an example in mind?
Let me see. There are many such examples. There may be even functions for which, let me see. So when I tell you, when I ask you this question, right, I give you this function, and I want you to differentiate it at time t equals 10. I don't really need to compute the derivative. I don't need to compute the actual value. I could just compute it approximately and get the value out really quickly, right? So imagine that the derivative of this is too complex for you to evaluate. It takes a lot of time, right? In which case, just evaluating the function, subtracting the two values and taking a delta would be much faster, right? You could do it that way too. Yes? Always throw what? It gives you that, but there are some toolkits which will not. This one will, but there are others which do not. Right? It's a question of where you want to do it. If you are okay with an approximate gradient, go with it. It's perfectly fine, right? So note again that this is all based on machine precision, right? Nothing is going to be perfectly accurate. There are floating point numbers which will always have errors. So this is all within machine precision. So it doesn't really matter. Now imagine you had to publish a paper in Annals of Math, and you had to find a derivative. Then you would do this because you want an exact answer. Yes? Is the difference clear? Yes? The numerical one is, it depends, I would say, on the implementation. Differentiate y equals x square analytically. Like how hard is it? Right? 2x, there's nothing to do. So it depends on the problem, I would say. There are some functions which are hard to differentiate, especially finding minima. So it's not just about finding the derivative. You want to set it to 0 and solve for that efficiently. How do you do that? Right? So that analytically it may not even be possible. Because these equations can be really hard to solve. So then you would just make a different optimization method. You will see about this in optimization. Is it clear? Okay, so yes.
For data science or for machine learning algorithms, do we really need this kind of functions like integrated?
So okay, of course. Like let's say you want to solve something like how do you think all of your machine learning models are optimizing some smooth surface? So you want to find the minima of something, right? Now you may not do it, but suppose you're a machine learning scientist at Google. They give you a complex objective function that you want to minimize, and your machine learning algorithm is going to be based on that. how do you compute the minimum of this function?
If I'm writing a machine learning algorithm myself, then I might use them. Otherwise, we're simply using the library.
Well, I mean, I would say it's a question of what scale do you want to be on. It's good to have depth of knowledge in terms of how these algorithms really work, because otherwise when they don't work, you will not know why it doesn't work, right? So you need to know what. So suppose I'm doing something like logistic regression. Logistic regression optimizes something called log loss. I need to know what the derivative of log loss is to ensure that I can actually see it happening. Or how do I know that it is working, right? Note that in several problems in the industry, you may not use log loss as is. You might make a modification to it. Now you will have a different derivative to compute, right? Which will be some variant of the log loss, but not the same. Then what will you do, right? So it is always a good idea to have a basic understanding. Yes.
Sometimes you want to minimize an objective function, you don't even know what the objective function is. So then you really need to do numerical.
Yeah, exactly. So you don't even know what it looks like sometimes. It's very hard. The error surface is very, very complex. You may not be able to compute the different derivative analytically. The same thing will happen. So log loss may not be differentiable, right? Like some of this may not be differentiable. So what do you do? So what about this function? Like you might have piecewise functions that you want to optimize over, right? They are not differentiable at this point. Then what do you do now? So there are methods to do that. They're called subgradient methods. Search for it online, you'll get it. Okay. Is this clear so far? All right. So we talked about Scipy and we talked about how this is useful. Right. Now visualization. So matplotlib is our library for visualization. It is built similar to MATLAB. Very easy to draw scatter plots, charts, histograms, lines, curves, whatever you want. Here's a very quick example. Now this is a fancy one, but we don't typically have to do anything of this kind usually. But look. From MPL toolkits.mplot3d, this is a bunch of imports from matplotlib. This is the function you want to plot. This is a 3D function. So it takes two parameters, x and y, and returns z. Yes? Phi m and phi p. Oh God, here we are. All right, so let's see. This is some complicated function, maybe from a physicist, right? We specify where to evaluate these functions from, 0 to 2 pi, right? And 100 such things. What does np.linearspace do? It produces 100 equally spaced points between this interval. So what are 100 equally spaced points between 0 and 1? 0, 1, 0, 2, whatever, right? This will produce that. Then then all we have is we put this into a form of a mesh grid. We plot it. So now look at the API. So all we have to do is figure out what the API looks like and call them, and you will do the job, right? So ax.plotSurface is the workhorse. It takes in three things, x, y, and z. X and y are the coordinates that we want to evaluate the function on, right? So it's something like evaluated at point 1, and z is the actual evaluation, right? So x, y, and z. So we remember that if you want to plot something in 3D, you have to give three things, x, y, and the height, right? We're giving all of those three things here. Where was it? ax.plotSurface, yeah? This guy. What does alpha do? Alpha is just setting the transparency of this color here. You see this blue thing? This blue thing is essentially light because alpha equals 0.25. If alpha equals 1, it will be dark blue. So it is just telling you how transparent this thing looks like, okay? This is telling you what the strides must be. So this is saying go in steps of 4. So just show me how, like these points here are in steps of 4 in some sense. So you can just see how this curve looks like, okay? So just look at the API for matplotlib and you will get all of this with examples and demos, okay? The entire code is available online. I'll show it to you. But this is just a very quick understanding of what you can do, yeah? You can set limits again. So you can set limits on what the x-axis must look like, what the y-axis must look like, and the z-axis must look like. So x limit 3D is saying the x-axis should go from minus pi to 2 pi. The y-axis should go from 0 to 3 pi. And the z-axis should go from minus pi to 2 pi. Yeah? That's all. We'll see this very quickly. But now comes the most important part. We come to, we'll apply all of these things, or at least most of them, to solve a problem. The question is, are boys taller than girls on an average? Right? So how would you solve this problem? Yes. What are the processes that you would do? What would you do? So you are at a company. You're actually at a medical center, right? You're a doctor there, and you are doing research on the growth development of humans, right? Now the question that is asked is, this is way back in the 12th century, guys, so whatever. So are boys taller than girls on an average? How do you do this?
Collect data for girls, collect the data for boys.
Okay, then what?
Then one is we can find the average height of both.
Okay, and then what?
That would be the basic thing, and then compare it.
How do you know if it is, what is your hypothesis? Are you going to say they're equal? Are you going to say there is no difference? So as you mentioned before, in a scientific method, you have to have a testable hypothesis. What is the hypothesis you're testing? Formalize it.
And our hypothesis is that there is no difference between boys and girls. And my alternate hypothesis can be that boys are actually taller than girls on an average.
So your hypothesis that you want to test is boys are taller than girls.
Yes.
On an average.
Yes.
Okay.
And my null is that boys and girls.
Forget about the null for now. Let's just talk about the hypothesis. Okay. Then what would you do? So we get the data, we form a hypothesis. Then what?
And start looking at the data and start the computation, whatever statistical method that you want to put in.
Okay, we'll see what statistical methods, and then you will interpret the results. Okay, let's do all of this in 20 minutes. I have how much? 220?
Yeah.
Okay, good. We have time. Let's go back to children. Here we are, guys. Okay. We are given the, so this is the question we're answering, right? Are boys taller than girls on an average? Yes? But we are make it more specific. We say, let's look at different ages. So at 2 years, 9 years, and 18 years. So I track a bunch of children from 2 years, 9 years, and 18 years and look at their heights at different points in time, right? So this is what I look at. So I have a bunch of children and I measured their heights at different ages. This was loaded from a Pandas frame. You see this? There's a CSV file which I just loaded. And it tab separated. Separator equals tab, T, yes? I load it. So let's load this. Boom, boom. Oh my God. Sorry. Yes. Boom. You see this? These are all in centimeters, yeah? So boys at age 2, this first guy is 90.2 centimeters. Girl at age 2, the first girl is 83.8 centimeters, right? Yes or no? What do you see here? For some reason, I didn't measure the heights of these people from 26 to 31, right? For boys, right? So now I have some missing values here. Now I could just ignore them. So when I compute the mean, I should not compute these using these missing values. I don't have to have nans there. Yes or no? Yes. So let's see how that works out. So now I'm here. I insert a new guy. Let's see if this works. df.describe, right? So there might be a bug in this, but we'll see. There's a bug in Pandas, which is what is happening. But you will see that it creates the mean, standard deviation, and minimum for all of these things. So at age 2, the boys at age 2 there are 26 boys at age 2. You see this? Their mean height was 88.4 centimeters. The standard deviation of those guys was 3.03 centimeters. The minimum was 81.3, the maximum was 92.2. Yes? Do you see that? For age 9, you see a different number, right? Now look, again, for boys at age 2, the mean was 88.4. For girls at age 2, the mean was 87.4. Does that mean that boys are taller than girls on an average? Okay, we will see how to formalize this again. But do you get the idea of how we can very quickly compute summary statistics for this thing? Yes? Now I want to plot these histograms of different boys and girls at different ages. Yes? So here we go. What is the x-axis? Histogram. Yes. What is on the x-axis? Heights. What is on the y-axis? Okay. So what is this telling me? What does this plot tell me now? There are two plots here. Do you see that? Boys at age 2, girls at age 2. And this is the distribution of their heights. Do you think they are vastly different? So on an average, what is the average here? We just saw it on top.
88.4 and 87.4.
Yes, they're somewhere here, right? We'll see that, we will actually see with a better visualization that there's not much difference. You can do this for all of them, right? Boys at age 9, girls at age 9. How do I do this? Note again, this plot histogram function is very, very simple. What does it do? It takes in a data frame and the columns for which you have to plot a histogram. Yes? It extracts out the columns. df of columns is just the data for those columns, right? So if I pass in something like boys underscore 2 and girls underscore 2, all I'm going to get is those two columns out. And then I just call dot histogram. See, Pandas has a histogram function already built in. Yes?
So does Pandas by default ignore NaN values?
Yes, it does. Unfortunately, in this describe function here, you will see that there is a bug. The 25% gives you an NaN, right? So in Pandas 0.18, that bug was there. It is fixed. This machine was not upgraded to it, but it is fixed. So what you will see is usually when it computes summary statistics, it will ignore nans. But this is a manifestation of a bug. And this is also a good point for you to note. So when things don't agree with your intuition, check the data, right? So here you see very clearly that the 50th percentile cannot be nan. Right? So there must be something wrong with either the computation or the data. The data is fine. So something is wrong with the computation, which means Pandas is incorrect, right? It's always good to have a double check. Yes?
So if I want to replace the nans in an entire table with something very specific.
It's very easy. So there is a method to do it. You have to just search for is nan and then replace it with 0.
But 0 will skew.
I know. So that's what I'm saying. You have to decide what you want to do. Replacing the 0 is not the right thing. Yeah. You will see all of these as the actual values with nans removed. So imagine those rows didn't exist. See, if these things didn't exist, what would be the sorted, the 25th percentile for all of this without the nans? That would be the answer.
In that case, you would not even know that there was some problem in the data. Here, just by looking at it, you'll at least know, okay, since it's
There is no problem with the data. It is just that, so you collected the data, right? And you know that you didn't collect data for so many things. So there is a way to do this. There's a default value which says keep NA. If you say keep NA, it means it will keep the nans. Right now, keep NA is set to false, which means that it will remove them. So it depends on what you want to do, right?
So Pandas has this thing, right, that it will, the histogram function that is inbuilt with Pandas, it handles the NaN, right? If you put in matplotlib, it will.
Yeah, it will not. That's what I'm telling you. So it will do it.
You choose like whether you go with the plotting that is like inbuilt with the Pandas, or you go.
So you go with Pandas if you want to do very quick analysis. If you want to do custom plots, then go with matplotlib. When I made custom, it means you want to change all of this behavior. And I'll show you how that might be done too. Okay? So I'm plotting all of these histograms in pairs, right? Boys and girls at age 2, boys and girls at age 9, boys and girls at age 18. Okay. Okay, I showed you how this DF describe works. Now, I have a question. So how do I know? I can compute the means of these guys. I already computed the mean. The mean height for boys at age 9 is 136. The mean height for boys for girls at age 9 is 135. Is this difference? Is there a difference? Is this difference something that you are going to make a claim saying yes, on an average at age 9 boys are taller than girls?
Well, you can't tell unless you do the analysis.
That's what I'm saying. So how do you do that? So now I want to ask the question. Are you familiar with how to do that? Okay, is everybody familiar with this idea? And how do you, like, yes, anybody who's not familiar with how you might do it? Okay, I will explain this in a very short toy experiment, but we'll see how to do it. Boys 18 and girls 18, look at this. The mean is 180.03. For girls, it is only 166. Now is the difference significant? Yes, and we'll see how this works. But first, let me get into a very quick review of what significance looks like. So I have a coin. I have a coin which I tossed 100 times, and I saw, let's say, 67 heads. Okay? I have a coin which I tossed 100 times. I looked at how many times I got heads when I tossed this 100 times. I got 67 heads. Is this coin fair or biased? That's the question you want to ask. Yes? Very similar to what we had before. Okay. Is this coin fair or biased? Now for this, it is not clear just because I saw 67 heads that the coin is biased. Why? Because even if the coin was fair, that heads and tails have equal probability of coming, you could still in some experiments see 67 heads. Yes or no? Does everybody agree with that? How do you know that? So let's see. So in this particular, the way to test if a coin is biased or not, in some sense, is to look at this. You take your assume the coin is completely fair for now, right? Toss the coin 100 times and count the number of heads. Do this a large number of times. Let's say I do this 10,000 times, right? If I do this 10,000 times, I'll get the number of heads I see in each of these experiments, assuming the coin is fair. That is going to tell me the probability, the distribution of heads, assuming a fair coin. Yes? What does it look like? So in this particular case, here I am. What am I doing? I'm essentially simulating all those coin tosses. 100 coin tosses, counting the number of heads, 10,000 times. Yes? So this experiment of tossing a coin 100 times and looking at the number of heads is repeated 10,000 times. Simulated, right? We get the number of heads. Let's look at what it looks like. So there are 56 heads, 54 heads, 55 heads, right? First trial I got 56 heads. Then I got 54. I got 47 also. I got 51. I got 42, 58, 53, right? A bunch of these things. Let's say we plot them. This is the distribution of what you might expect, assuming the coin is fair, right? So if the coin is fair, I would see this distribution, the blue one, yes? The mean is 50. You see that? The mean is 50. Why is it 50? Because the coin is supposed to be fair. Yes? Now, this is what you might call a null hypothesis in this case. Why is it a null hypothesis? This is assuming there is no effect. Let's say the coin is completely fair. So assuming the coin was not biased, what would be the distributions of these heads that you would have observed? Right? That is what you're comparing against. So now this is the blue thing is what you would observe. The mean is 50. What did you observe? 67. Right? What is the probability of seeing 67 heads, assuming the coin is fair? How do you compute that? Visually, how do you compute that? What is it? The 67, where 67 is seen is this red line here. That's what 67 is. Right? What is the probability of seeing 67 heads or more? Assuming the coin is fair. Is it small? Is it large? What is that value exactly if you want to compute this? It is the probability mass here, right? After the red line. You see this blue region after the red line? Remember that this is a probability distribution if you normalize, right? The probability of x is a random variable, which is the number of heads. What is the probability of x greater than 67? That's what you want to compute. How do you do that?
It's 1 minus x less than
Which is what? Which is all of this region, right? Which is essentially the same as this guy, because all of this sums to 1. 1 minus this part is this tiny violet region. Does everybody see it? Yes or no? So this tiny violet region is the probability of seeing 67 heads, assuming that coin is fair, which is extremely small. So if this value is really, really small, you can pick a threshold. Most people pick a threshold of 0.05, 5%. Right? So if it is less than 1% or 5%, then you can claim that with very high confidence, your coin is biased. Yes?
So, but I mean, like, is that the formal, that you just literally just pick a low percentage and then you say, oh, if it's lower than this percentage?
Yes, so most people pick something, if you're in statistics or in science, you pick something which is 0.05. Some people will say even lower, you may go in 0.01. There is no standard threshold to pick. Most people in the community will pick either 0.05 or 0.001. In physics, you might require it to be extremely, extremely low. So if you want to do this is the detection of the Higgs boson, guys. Okay, you have an experiment, you are detecting the Higgs boson. Now you have an experiment you want to compare against random chance. What is the probability value you should choose?
So how would you pick that as something where you don't simulate? So in the instance of the heights, you're going to say, okay, we have a difference of 1 centimeter.
So you don't necessarily have to have a simulation. You could have a hypothesis or a random a process which you claim is a null model, which is like, you might have an idea about how things might work if this thing was not true, and you could analyze what conclusions that would lead to.
Could you give me an example for the heights?
For the heights itself. So let's say this is what you do. Through biology, you learned that through analyzing biology and cell structure or whatever, you developed a model saying the heights of males is normally distributed, with a mean centered around 50 centimeters or whatever, 80 centimeters, with a standard deviation of 0.1 biologically, because there is a biological process that stops people from growing high above that. This has been obtained through analyzing how cells grow or whatever, right? you don't necessarily have to ask that question now. Like, so you don't have to do this simulation at all then. I give you something and ask, is this a height of a man or not? And you can tell me it's not, right? Because you have a different model. You don't have to do simulation, right? Is it clear? All right. So this is a very quick summary of what you mean by statistical significance. Now, if you go back, you will see that there is one caveat though. Note that don't use this thing blindly, because just because you got a low value, there are all kinds of effects you need to understand. The first thing is, and you can look it up later, but most people just don't. This probability that I computed here, this small thing, is called a p-value, okay? And you will note now, especially in biology and the life sciences, you'll see this term called p-value hacking, okay? John Oliver talks about it, if you have seen this, okay? So I'll just leave it at that. You go back and figure out whether it is useful and how it can actually be made more robust. Yes. So again, this is not a yes.
Is confidence a formal metric or no?
Confidence is a formal metric too, and this is one of the things that p-value. If you want to improve on p-values, you address it by giving what is called confidence intervals.
Okay.
But that's what I was suggesting. So I would suggest additional reading. Go read about confidence intervals and multiple hypothesis testing, and also p-value hacking. Okay. So moving back to our children's example, let me visually demonstrate to you that there is not much difference. So now here, I am plotting again the same set of boys and girls at age 2, but the histograms are normalized. You see, this thing will now sum to 1, right? The earlier one were 2 different plots. Now here they're on the same figure, and they're going to overlap. And this is the blue line is the mean height for boys. The red line is the mean height for girls, right? You see that? You will see so much of variance. That's what we were discussing last class, right? Is this due to random chance or is this due to an actual effect? Yes or no?
Yes.
Do you recollect that thing, the printer analogy, right?
Yes.
Okay, same thing. You see this large variance, and the means of these two guys are here, right? So there's not much difference, and we'll know how to do that. So if you want to actually quantify this difference, there is something in statistics called the paired t-test. Look it up. It is used to distinguish whether the difference in the means of 2 samples is statistically significant. The same example I gave you before. Paired t-test. I'm sorry, what? It's a very old test. It's developed by Fisher, so who knows? But maybe you're right. Fisher developed this when he was trying to analyze the geographic variation of crops, by the way. Old story. All right, so we can do this at age 9. So look, again, the p-value is really, really high, 0.28. It's not 0.05. You see this? So if you want to analyze the difference in the means and you compute a p-value using that test I told you about, right? You'll get a p-value of 0.28, which is not significant under any significance level. So 0.05 is at least the minimum. You want to use 0.05. Yes, it is higher, so which is why it's not significant. Something that is lower is significant. Right? Everybody understand this or not? Okay. Boys and girls at age 9 again. You see this thing? Same plot at age 9. Right? No difference. 0.38, even worse. Right? But at age 18, watch. P-value goes very low. Yes? And there is a huge difference. So now you can make the claim saying that the average height of boys is greater than the average height of girls at age 18 with a significance level lower than 0.05. Yes? Do we agree with that statement? What about age 21? Can you say anything about age 21? Okay, good. So you can't do anything without that because you don't know if there's a growth spurt suddenly. Right? Biologically, there could be a growth spurt after age 18. You don't know. All right, so I think we are done with this. Any questions, feel free to ask me again. Okay. You remember the coin example? the p-value there was the amount of probability of having this